Okay, so welcome again to another session of the seminar of the International Institute of Physics, and it's a great pleasure to introduce Konstantin Zarembo, who is currently at Nordita in Stockholm and shares time with Niels Bohr Institute in Copenhagen. Kosta defended his PhD at the Stiklov Institute, Mathematical Institute in Moscow. After that, he spent some time as a postdoc at the University of British Columbia in Vancouver. And since 2001, he's a professor he was a professor at Uppsala until he moved to Nordita in 2010. And in the middle, he spent also 2 years as with the director of research appointment at the École Normale Supérieure in Paris. So Kosta is very well known for his work in quantum field theory, string theory, and integrability. So he is in particularly known for different tests of holography or IDS-CFT correspondence, in particular, showing that calculations on two sides of the correspondence give the same results. And with his work with Joe Minahan also is very well known, which inspired many work on search for integrability structure in IDS-CFT correspondence. Today he will talk about fate of the chiral symmetry break in Gross-Neveu model.
Oh, after such an introduction, I can just bow and walk away. Okay, so today's talk is based on a work with Waldemar Melin, Yuta Sekiguchi, Paul Wigman, and myself, and also work in progress with the same authors. So our motivation comes from, actually, it's a motivation for the work that was motivation for our work. And it comes from QCD, understanding what is the phase structure of strong interactions at finite temperature and finite density of baryon charge. And in QCD, chiral symmetry plays a decisive role in the low energy physics. So in the vacuum, it is broken, but then and the order parameter for chiral symmetry is the chiral condensate, which melts at certain temperature, and then the system undergoes transition to the quark-gluon plasma phase, and so this is phase diagram one gets. I downloaded it from somewhere in the internet, and well, basically this diagram is basically science fiction. No one knows how to compute all these lines, and understanding phase structure of QCD is very interesting, but mostly unsolved problem. So people turned to simpler problems where you can make analytical progress. So the problem here is that you cannot put this easily on a computer. There is a famous sign problem for that hinders Monte Carlo simulations of QCD at finite density of baryon charge. And so analytical methods also do not work because QCD is strongly coupled theory. So people try to understand simpler systems. And one such simpler model is the Gross-Neveu model. It's a one-dimensional theory, 1 + 1 dimensional, of fermions interacting through contact for fermion interaction with some coupling constant. And there are n species of Dirac fermions. So this n plays the same role as number of flavors in QCD. This theory is known to be asymptotically free. So the coupling runs strong in the infrared and becomes weak in the ultraviolet. The system undergoes dimensional transmutation as QCD. So there is no mass parameters in the Lagrangian, but mass is generated dynamically through RG running. And also this model has chiral symmetry that is broken in the vacuum. So the fermion condensate is non-zero. And so this model shares some features with QCD. In particular, its phase diagram looks pictorially very similar. There is a gapped phase, which is analog of the hadronic phase in QCD, where the Chiral symmetry is broken and Chiral condensate has non-zero expectation value. But then it melts at higher temperatures, and system undergoes a phase transition into fermi-liquid phase, where fermions are essentially massless. But then people discovered that at low temperatures but high chemical potentials, the system forms chiral crystal, something that cannot exist. That the lowest energy state in this region is a state where chiral condensate is modulated in space with certain period. So it forms spontaneously forms crystalline structure. But one-dimensional crystals cannot exist. There is a very simple argument that goes back to Peierls and Landau, and in particular, Peierls gave a very simple argument why crystals cannot exist in one dimension. So let me repeat it in 2 words. If you have a chain of atoms that can vibrate away from their equilibrium positions, and let's say these deviations from equilibrium are very small. But then if you look at the position of nth atom, these deviations, well, they add up, and just by large, how's it called? Large number theorem. I forgot. Anyway, so the sum of n random numbers scales the square root of n, right? And so no matter how small the individual deviation is, at some point, this integrated deviation of the atom from its equilibrium position will be of order of latest step. So at large distances, the long-range order will be inevitably disordered and will disappear. So more formal argument is known as Coleman-Mermin-Wagner theorem, and it has to do with the fact that the symmetry that is broken is continuous. So a crystal breaks continuous translation symmetry to a discrete symmetry. There is a Goldstone boson associated to this, which is just a phonon. And then there are 2 possibilities. So the Goldstone boson is massless field in 1+1 dimension, has growing logarithmic correlators, and so it destroys the long-range order as well. So there are 2 possibilities. Either it gets gapped, and then there is a finite correlation length, or it disorders the order parameter in a weaker sense, so that the correlations are algebraic, but they still decay, so there is no long-range order. So the conclusion that there is a crystalline phase in the Gross-Neveu model, it was obtained in the large n limit, which is equivalent to mean field, So the way out of this impasse is that large n limit and the long distance and the thermodynamic limit do not commute. And in fact, the system exhibits a long-range order. So if you compute it, if you are able to compute a 2-point function of the order parameter, the chiral condensate, then it will oscillate, but these oscillations will be modulated by an algebraic decay with a very small exponent that is parametrically small. It's order 1 over n. So this was observed in another variant of this model, which is, well, I don't want to dwell into details, but this picture is expected to occur in the Gross-Neveu model. And our goal was to understand it from the, well, maybe not rigorous, but from calculational point of view. But before, and we were able to do so because the Gross-Neveu model is integrable, and one can use beta-ansatz techniques to solve it. But before that, let me tell you how this conclusion about the Chiral crystal was derived, and just to say a few words about the Largian solution of the model. So, well, it's a very standard thing. You unwind the four-fermion interaction using Howard-Stratanovich trick. So the sigma field is on shell, it's just a chiral condensate. But then the idea is that you integrate fermions instead, and then you get an effective action for sigma, which is of order n. And so at Largian, the saddle point approximation for this effective action becomes exact. So basically, system reduces to the mean field approximation. So if you compute this potential, then one can see that it has a maximum at 0 and two minima at some position m that is at some value of sigma equal to m. And this is given by the gap equation. The gap equation is obtained by simply minimizing the effective potential. So on the other hand, the expectation value of sigma determines the mass of the fermion. So first of all, there is a symmetry here that changes the sign of sigma. It gets broken in the ground state. There are two ground states to that matter, and the position of the minimum is determined by this dimensional transmutation formula. So you need to regularize this integral, and the mass arises from out of the cutoff and the bare coupling. So if one adds a chemical potential, then the effective potential for sigma will change, and it will flatten with so if you go from this point with zero chemical potential and then slowly increase it, then the potential will flatten, and eventually the two minimum will merge, and what had been a maximum becomes a minimum of the potential. So it's a typical picture of second order phase transition in the mean field approximation. So the two minima disappears, and we get a single minimum at 0. So which signals that chiral symmetry is restored, right? Because sigma equals 0 means that we don't have chiral condensate. This is an Largian approximation. This is, yes, so there is some critical point here where this happens, where these two minima collide, and the potential loses its Mexican, well, it's double well shape. But this is not the end of the story, because if we now switch on temperature, and suppose we go from higher temperature to lower ones, then there is an unstable, one of the modes becomes unstable. This is, in a sense, this is a plasmon mode. So one can compute a propagator for the sigma field. So this is the next correction in 1/n that contains a fermion loop. And at finite temperature and density, the quantum of the sigma field develops a pole. So there is an propagating degree of freedom associated with it, and it has this funny shaped dispersion relation that has a minimum at some momentum. So this is energy, this is momentum, and the dispersion curve has a minimum that if we lower temperature, this minimum goes down, and at some point it hits 0. And then if you try to push the system even further down, then lower temperature even more, then in some range of momenta, the energy becomes complex that signals instability. So there is an instability scale at certain wave number. The wave of the field sigma becomes unstable. And so the minimal energy configuration then is a chiral wave. So it's, roughly speaking, it's a, I don't know, some, I wrote sign, but it's some periodic function of x. And so this is the origin of this phase that exists at sufficiently low temperatures and sufficiently large chemical potentials. Mean field theory predicts that the system will spontaneously develop a periodic structure of the chiral condensate. So the reason for that is actually well known, and it's known from, I don't know, from the 30s maybe, and is known as a Parel's instability. So the cause of it is that if you have a fermion or fermions, then basically the energetics is such that the configuration where the fermion is at half filling is very stable thermodynamically, whereas if you push the chemical potential up in the conduction zone, then this is not stable. This is energetically not very stable configuration, and the system will try to push the system. Well, if there is a way, if there are interactions in the system, they will try to rearrange it in such a way that it is back to half filling. So in particular, one mechanism for that, one famous mechanism, of course, is superconductivity, but in one dimension, there is a simpler way to gap the system, and it is related to creating a periodic lattice, right? So if there is an environment that can produce a periodic potential that affects the fermions, then they will simply develop the usual band gap, and so if this band gap lies near the Fermi level, then they will be back at half filling. So that's the mechanism behind the Parel's instability, and it appears in many problems in physics, in charge density waves, in one and two-dimensional condensed matter systems, polyacetylene, and also in Gross-Neveu model. So the upshot is that there is a, so here the environment comes from self-interactions, and it is just this sigma field that develops an expectation value that's periodic. Fermions feel this periodic potential and appear, and that produces a gap in their spectrum. So one can calculate things very explicitly here, and so there was a series of papers, notably by Thies, who calculated the properties of this crystalline phase. So there is a prediction for the critical chemical potential, and one can even solve for the shape of this chiral density wave, which turns out to be a connoidal wave, so it can be solved in elliptic functions. But as I already said, this cannot be completely true. So something should go wrong, because the one-dimensional crystals cannot exist, and so crystalline order has to be destroyed in some way at large distances. And our goal was to understand how this happens in detail. So a priori, there are many possibilities. So it could have been that the transition is not really a transition, but a crossover. That it happens only for very large n. So of course, this picture captures the behavior at very large n, and locally it should be correct. But so as we lower n, the origin approximation loses precision. So the question is there a critical n below which the transition doesn't exist? So how accurate in general the origin approximation is, and if there is a gap, and so on. So all these questions can be addressed in this model analytically because it is solvable by beta ansatz. This Gross-Neveu model is an integrable theory, and its exact spectrum and exact S matrix are known exactly. And once you know the exact S matrix, you can also build in exact thermodynamics using thermodynamic beta ansatz. So in principle, everything, all ingredients are known. It's just a question of grinding it through the machine of thermodynamic of TBA. So as usual, the way to understand to understand this exact spectrum and exact S matrix is from symmetries. So they were derived by Zamolodchikov and Zamolodchikov from integrability bootstrap. So you impose all known symmetries and on the S matrix, and in integrable systems, S matrix factorizes into two scatterings, and then from symmetries you can just calculate what the S matrix is. Okay, so what are the symmetries of this problem? There is a global O to N symmetry, and only SUN part of it is manifest in the Lagrangian. So we started with n Dirac fermions, and obviously there is a symmetry that rotates these fermions, but it's actually bigger because you can decompose each complex fermion into Majorana components, and the symmetry that rotates real and imaginary parts of the fermion still leaves the Lagrangian intact, and so the total symmetry group is actually O to N. There is also chiral symmetry, which is a discrete symmetry here. So it multiplies fermions by gamma 3, analog of gamma 5 in 2 dimensions. So that doesn't change the kinetic term, but it changes the sign of the chiral condensate, and that has to be compensated by the change in the sign of sigma. So this acts on both psi and sigma. Also, n here should be bigger than 1. So one, of course, can consider a model with just one fermion, but that model is CFT. It's equivalent to the Thirring model, and it has very different properties. It doesn't have the dimensional transmutation because its beta function is 0. So the beta function is proportional to n minus 1. So we'll always assume that n is 2 or larger. Any questions here? Yes. Well, so there are 2n components so fermion has 2n components if you count real and imaginary parts. So and you can rotate, you can put them in one vector. It's a real vector now. So the symmetry that rotates it is O2n. So, well, one degree of freedom that's obvious from the large analysis is a massive fermion. But interactions are still important. So they're suppressed by 1 over n, but they are attractive. So fermions can form bound states, and if you compute the simplest leading order amplitude in 1 over n, then it turns out that it is attractive in the anti-symmetric channel and repulsive and symmetric. So even weak attraction is enough to form bound states in one dimension. So anti-symmetric combinations of fermions will form bound states. So a more refined analysis shows that this number of bound states is finite. So up to n minus 2, they can have up to n minus 2 constituents. And from integrability, one can derive the mass formula. That's this typical sign formula that arises in all integrable systems. If you look more carefully at it, you'll see that the binding energy is indeed 1 over n effect. It's approximately linear in the number of constituents with up to small corrections in 1 over n. And then, in addition, there are also solitons. So since the system breaks Z2 symmetry, Chiral symmetry in this case, there are two vacua, and there can be domain walls between this vacua, right? So can interpolate between state with sigma equals minus m and sigma equals plus m. Well, in one dimension, the domain wall is a particle. So these particles, well, what can give a semi-classical description of this of the domain wall, and obviously, since this macroscopic classical configuration of the sigma field, the action for sigma is proportional to n. The mass of the soliton is very large; it's of order n. Again, one can find the exact formula for it, and so so in addition, there's also solitons. So important feature of solitons is that it harbors topologically protected fermion zero modes. So if you consider a fermion on top of the soliton, then there will be upper continuum, lower continuum, but in the middle, there will be a normalizable bound state with exactly zero energy, and this is protected by topology. So that's a feature that cannot be changed by quantum corrections. So since there are n fermions, there will be n bound states, and each of them can be either empty or occupied. And since the energy of this state lies exactly in the middle, it has zero. The energy is zero. So leaving it empty or filled doesn't change the energy of the system, and so this means that the soliton has an internal structure related to how we assign occupation number to the zero modes. So here is an example. It's let's say take O6 model. There are 3 Dirac fermions. So each soliton will have 3 zero mode levels, and there are basically 4 possibilities to fill these levels. So in general, for arbitrary n, we'll have n zero modes, and there will be 2 to the n states. And 2 to the n is actually the dimension of the spinor representation of O to n. In fact, the spinor representation is constructed precisely in this way. We take fermions and using Clifford algebra, we can construct spinor representations. So the upshot is that solitons transform in the spinor representation of O to n. Then one can also argue that that solitons also carry baryon charge, by baryon charge I mean fermion charge. So that is assigned. So 1 unit of baryon charge is assigned to the fermion. But for the soliton, we should assign the baryon charge depending on how its zero modes are filled. And there are many ways to arrive at this assignment. So we should start with -n/2, and then for the empty state, and the largest baryon charge is n/2 for all levels filled. So one simple way to argue for this assignment is that this is the only one consistent with particle Hall symmetry, which is relativistic systems is a must. So this has to be symmetric. And of course, if we fill one level, we raise the baryon charge by 1. But as a result, the baryon charge is actually fractional. So it's if n is odd, like here, then solitons will carry fractional charge 3/2 compared to the charge 1 fermions. So here is the summary of the spectrum. It neatly fits into the Dynkin diagram of O to n. So this line corresponds to the bound states, and these two spinor nodes correspond to solitons. So the basic vector representation is a fermion with mass m, and it has baryon charge 1. Then bound states have maximum baryon charge a, number of constituents. There is a mass formula for them. And finally, there are solitons with baryon charge n/2, and there is also some mass associated to them. Sorry? So each particle corresponds to a fundamental representation. So only fundamental representations appear in the spectrum. So fundamental representation meaning that it's associated with one particular node in the Dynkin diagram. So the bound state of with n constituents corresponds to the 8th node on the horizontal, and then there are two spinor nodes, which are solitons. So just from looking at this picture, one can draw a lot of conclusions about the phase structure of the model. Good question. It's here. It is the filling fraction of zero modes. So you see, these two states are assigned chirality 1, and this chirality -1. So if the number of occupied fermion levels is odd, then we assign positive chirality. If it's even, let me see. Actually, it's incorrectly written here. These two states belong to representation S with positive chirality, and these two states belong to representation with negative chirality. It has nothing to do with space-time chirality. So it's just purely internal notion related to the zero modes. All right, so now suppose that we want to consider a state of the system at finite baryon density, so at zero temperature. Well, in some rough approximation, we just distribute, let's say, n particles of type I. So there are many, as explained, there are many types of particles possible, bound states, solitons, etc. And original fermions. So all of them carry baryon charge, so the total baryon charge will be given by the number of particles times the baryon charge of each particle. And the same with energy, it will be, in the simplest rough approximation, it will just n times the mass of the of this particle. So the question is, what is the smallest, what is the state with the smallest possible energy given total baryon charge? And looking at these formulas, it's clear that this is achieved by the smallest ratio of mass to the baryon charge for individual member of this configuration. So we need to look for the smallest ratio of mass to baryon charge. Well, the easiest way to do it is plot it graphically. So here is the picture. So this axis is the baryon charge. This is mass. And I just draw here these two. This is the graphical representation of this table. So here are the bound states. Here are the solitons. And it is immediately clear that the elementary fermion is not a good choice, right? So it's much better to put baryons in the bound state. You gain binding energy by doing that. But what's remarkable is that it's even more, it's even better to put the baryon charge inside solitons. So solitons are most energy efficient. They have the smallest ratio of mass to charge. And so the ground state of the system, if you drop some number of baryon charge in the system, you might think that, okay, so the first approximation, you would think that this will be just fermions with some density distributed in space. Then upon a thought, you might imagine that they will form bound states. But in practice, what happens is that they will create a soliton lattice. So it's energetically favorable to distort the sigma field in such a way that it produces this periodic structure well, if the distances here are very big, we can just treat this as a standalone soliton. It will have zero modes, and the zero modes can accommodate baryon charge. So all baryon charge will reside in the soliton zero modes. So this is, in a sense, is a simple explanation of Peierls instability. And the system itself prefers to be in the state where there is a periodic lattice that puts the fermions in the mid gap. So they will all sit in between the this Dirac continua. So this is this is in a sense a classical picture, but since we have a full solution of the model, we can also describe it exactly using beta ansatz. And then beta ansatz is basically agnostic to what particles you're dealing with. You just have some particles with certain mass, and it's convenient to parameterize them using rapidity, because then the S matrix is a function of a difference of rapidities. And we simply, treat these particles as interacting fermions. And beta ansatz, particles behave always as interacting fermions. So they occupy some Fermi interval with certain density. And it's actually convenient to introduce the energy variable. That's the energy of a hole that one creates when. So it's just an energy that that one gains by filling in these levels. It is modified by interactions, but in a way that is controllable because the system is integrable. And so let me give this equation without derivation, but its meaning is more or less transparent. So if you don't have this term, this is just the energy of a free particle with the chemical potential mu and mass m and rapidity theta. So then pairwise interactions between particles create this term. So it depends on the scattering phase shift. And well, from beta equations, you can derive that the only effect of interactions is just to shift the energy by something that depends on this matrix. So everything boils down to solving a single integral equation. And once the solution is known, one can compute the free energy by integrating this function, which is known as pseudo energy. Also, the condition, so this also defined on a finite Fermi interval. And the Fermi points are simply the points where the energy crosses zero. So these two conditions form a full set of equations for epsilon, which is just a matter of solving it analytically if we can, or we can put it in a computer. That's a very simple equation. But then, of course, the solution to this equation exists only if the right-hand side is negative somewhere. Otherwise, the particles will not condense. And it also means that the chemical potential must be larger than mass. So there is an activation point where chemical potential equals to mass, right? So it only then can it create particles. So the critical point is then where chemical potential equals to mass. So mass here is the mass of the soliton, and chemical potential of the soliton is the basic chemical potential for the baryon charge times the baryon charge of a single soliton. So it's mu times n/2. Equating these two, we get the equation for the critical point, for the critical chemical potential with the transition to this chiral density wave state occurs. And in the large and limit, it agrees with mean field. But this is a completely, it is an exact formula. It doesn't have any approximations. In particular, this solution is consistent for any n. So there is no critical number of flavors. This chiral transition happens for any n where the system is asymptotically free. So then, okay, here is this equation again. So one knows what is the mass of the soliton, what is the chemical potential, and also the kernel in this equation is known. It can be extracted from the soliton scattering matrix that was computed by Karofsky and Thun very long ago. So everything is known. Now, what we did is, well, we studied this equation also numerically, but it can be solved analytically, or if we take the large n limit. So then the kernel simplifies, and both the kernel, the mass of the soliton, and the chemical potential are proportional to n. So n scales out of the equation, and we get actually a singular integral equation. So this logarithmic singularity arises just because of the large n limit. And this equation can be solved analytically. So the way to do it is that we differentiate once, and then we get an equation that is very familiar from matrix models. And this has a typical square root solution, which resembles Wigner semicircle law. except that it is written in these hyperbolic variables. So then using the condition that it should cross zero at precisely at B, we find that the dependence of the Fermi rapidity on the chemical potential. So it can be written as an indirect function. So this is the complete elliptic integral of the modulus that is the inverse of the cosh of B. So there is a formula for the that determines B once mu is given. And well, there is a phase transition point where mu goes to the critical to the critical value, to the activation point, and there is some rather unusual square root scaling, which is also logarithmically enhanced. And in the opposite regime, where the chemical potential goes to infinity, the Fermi rapidity is logarithmic. And this regime is perturbative, so we should be able to match with the usual perturbation theory. So that effectively, because of the asymptotic freedom, the running coupling should become small, and we can identify the running coupling with the inverse of the Fermi rapidity. So this is because the coupling constant depends on the scheme, and one can show that there is some scheme, call it integrability scheme, where the coupling constant is exactly equal to the inverse of the Fermi rapidity. And so then at weak at large chemical potential, the coupling becomes weak. It is logarithmically, it behaves logarithmically, but it goes to zero. And it blows up at the critical point where Fermi interval shrinks to zero, and so the coupling goes to infinity. So in a sense, this when we change the chemical potential from infinity to the critical value, the system goes from weak coupling to strong coupling. So then one can also compute so this pseudo energy is, as I said, this has a physical meaning of the energy of a hole in the distribution of solitons. One can also compute their momentum. That now theta becomes a label because it's just because these are solutions of some nonlinear equations. So the dispersion relation should be found by solving for epsilon and p. So one can compute momentum as well, or actually better say its derivative. So it also has the inverse square root. Anyway, so if one goes through the algebra, one can derive the dispersion relation of the holes. And it is given by this, so it's again an implicit formula. So one can, of course, one can integrate this. So this should be, there should be d epsilon here. And it, yeah, so one can simply integrate it. But this integration of the right-hand side gives an elliptic integral. So we can solve it, but in terms of elliptic functions. And then, in addition, one typically writes the dispersion curve as energy as a function of momentum. So then one would need to invert elliptic integrals. That's not a fun thing to do. But well, it's easy to draw what this dispersion curve will be, and it starts linearly at small momenta, and then it goes to some maximum near the preon zone, and it's periodic. It's periodic and p. As expected from this picture, qualitative picture of chiral crystal forming in the background, so what we get is a typical dispersion relation of a phonon in such a crystal. In particular, this parameter Cs is nothing but the speed of sound. Again, it can be computed as a function of chemical potential. So this K and E are elliptic integrals, K prime is complementary modulus. And there was a formula that related K to mu. So one needs to solve this equation for K, and then this will give you the speed of sound. Yes, and then this dispersion curve simplifies at the critical point where it becomes precisely the dispersion of a harmonic lattice, because solitons then are well separated and approximate the force between them by harmonic potential. And so what you get is this textbook's formula for the dispersion with this sign of P, which is Formula 101 in any condensed matter textbook. So the upshot is that holes in the Fermi sea of solitons are actually phonons in the chiral crystal. The speed of sound, it goes to zero logarithmically. Well, it's as a square root, but enhanced by a logarithm. And then it quickly grows up to the speed of light. And also, in one dimension, there is no difference between the conformal. So we expect that the system becomes conformal at large densities because they're because of the asymptotic freedom. But then in one dimension, conformal speed of sound is actually equal to the speed of light. You may know that in 3 dimensions there is a factor of 1 over square root of 3. But in 1 dimension, this is just 1. So it does behave as expected. One can also compute the dispersion of the fermion excitation. And then it turns out that, so the fermion is just elementary vector particle of the model. To find the dispersion relation, we need to know the fermion soliton phase shift, and then we just solve the same equation as for solitons. But apart from fermions, we expect to find holes as elementary excitations. And what is a hole? Well, in this simplified picture of the soliton crystal, if you take out one of the fermions out of the zero modes that are all filled in the ground state, then one of the solitons changes chirality. And so the hole is actually a soliton, but of the opposite chirality. So for that, we need the scattering phase shift for solitons and chiral and antichiral solitons. So I'll maybe skip the details, but the picture that you get is also very much expected. So the fermion dispersion is a distortion of the linear dispersion curve. So they behave as if they are massless fermions. But the chiral crystal creates a gap. It's just the band gap. And because of integrability, this is actually a finite gap system. So strictly speaking, so we get all of the functions type that we get is elliptic functions, and they typically rise in two-gap Schrödinger equations. And indeed, this if one draws a charge conjugate of this will have another symmetric gap. So this is secretly a two-gap system, and there are no other band gaps in the model. But these curves, but we got them from beta ansatz without thinking about Schrödinger equation or soliton lattice or anything like that. So the gap itself, well, it starts at finite value at the critical point, which is just a fermion mass. So it's equal to m here, as expected. The gap is just the distance between actually, I think this with this definition, this should be 2m times e to the minus b. So it should be just the distance between the upper and lower Dirac continua. But then it decreases, and at large chemical potential, it behaves exponentially with the coupling with a large exponent. So in the typical non-perturbative effect that you would expect would be e to the 1 over lambda, and this is suppressed even more. So this is very, very small effect, and it remains non-perturbative even in the regime where the coupling constant is very small. So you will not be able to see it at any order in perturbation theory. So I think my time is up, and here are the conclusions. So we can solve for the phase structure of the Gross-Neveu model exactly at any n using thermodynamic beta ansatz. So here we restricted ourselves to the line of zero temperature, and there is a quantum critical point associated with condensation of solitons. And in beta ansatz, it has a very simple description. So in particular, one can predict the position of this point, the critical chemical potential. This formula simply follows from the mass formula of solitons. So high density phase has quasi-long range order. We got only indirect evidence for this from beta ansatz. We didn't compute any correlation functions. But there is a massless phonon, and the fact that phonon excitations don't have a gap immediately mean that the Goldstone boson will produce the quasi-long range order. In particular, there are no symmetries broken by this phase, as in accord with Coleman-Magman-Wagner theorem. So phonon remains gapless, and fermion spectrum is always gapped. So that's the features that are expected on general grounds, but we can quantify them using beta ansatz techniques. So it would be very interesting to understand what happens at finite temperature. What is what we are trying to do now. Thank you very much. That's all I wanted to tell you.
Interesting talk.
So great talk. How does soliton looks like in the bosonized language? Like you use fermions, but
yeah, good. Yeah, it's so for this model, bosonization doesn't work because the fermions, because for some technical reasons, which I frankly don't quite understand. So what people did is they studied the model where the fermions are complex. It's called Chiral Gross-Neveu model, and the chiral symmetry there is U1. There one can bosonize, and there one finds there is no phase transition in that model. It's always in this chiral density wave phase, but there one can explicitly show this quasi-long range order just from bosonization by writing some kind of effective equation for the bosonic counterpart of the fermion.
I see. Thank you.
So thanks for the nice talk. On one of the first slides, you showed us results that they obtained this crystalline phase in the Gross-Neveu model at large n, right? At infinite n.
Yes.
So, but integrability, this crystal phase is actually a quasi long-range order phase, which does not have any troubles with the usual theorems. So, but then I wondered, like, if I define my path integral of my quantum field theory at strictly infinite n, say, like taking n to infinity, this is somewhat showing that it contradicts those usual theorems of quantum field theory. Like, is this a general thing? Is there other examples where if I evaluated my field theory as strictly large n, but then...
this is generic. This was noticed by Witten in 1978.
Okay.
And it's a very simple thing that if you take large n limit, means that n is bigger than everything. Like, for instance, it's bigger than the volume of the system. And so these theorems don't apply because they are proven by looking at very large distances. But if you have a parameter that's bigger than ever, than the distance you're looking at, then of course they don't apply.
Okay, thanks.
Well, I'm a little bit confused still. So what exactly is quasi long range order here? Because I thought that most of the time you actually were proving that there's the Chiral crystal.
Well, I mean, this Chiral crystal thing is in the beta-ansatz picture. It's just I don't know. It's an interpretation of the formula. So there is no, like, you feel the Fermi sea of solitons. If you think of this as just solitons sitting at certain positions, yes, there will be Chiral crystal. But in practice, what they are doing is putting solitons at certain momenta that interact, and beta-ansatz takes this all into account. So they need not be in this very ordered state where they are separated by some steps. But then this quasi-long-range order, I mean, this denominator arises from coupling to M massless field. So if you couple the order parameter to any massless field, you'll produce a damping factor like that. So once we have massless gapless phonon, it's clear that the correlation function should go like that. I don't know if this answers your question.
So it's basically you do have crystal, you have everything, but the only thing that tells you that it's not violating any theorem is that you have this damping in the correlation function.
Yeah. So if you look at this formula like this, and n is very large, then this factor is very slowly decaying. So the way the correlation function will really oscillate at so there will be some tail that so this would be a correlation function that will oscillate with some amplitude that slowly diminishes, right? So if you look at it locally, where this curve has a very very slow slope, a very small slope, then locally on any, finite interval of x, it will oscillate and as if it was a real crystal. But eventually this decay will win and the correlation function will go to 0. So there is no contradiction with the long range order will be destroyed.
What about the Goldstone bosons? I mean, you said there's no breaking of symmetry, but there's still
The Goldstone boson still exists, and that we can see from the beta answers very explicitly.
So what does it mean? I mean, you're supposed to break symmetry to have Goldstone.
Well, this is this.
So you should not call them Goldstone bosons, probably.
I don't know why not call it Goldstone boson, but it's just this Berezinski-Kosterlitz-Taulus picture of one-dimensional system with a long-range order, with weakly broken long-range order. It still has a Goldstone boson, but no symmetry breaking. Well, the correlation function goes to 0. So there is no, goes to 0 eventually, making many oscillations on the way, but it goes to 0, so there is no long-range order. The symmetry is not broken. The condensate that you would define by computing well, there is still a phonon in the system. It has no gap, but symmetry is not broken.
I think you probably understand that you start from a point where Dargian limit where it is broken, and you call it a Goldstone boson, but then you change M, and the same mode persists, and it has
Yes. Yeah. Oh, I mean, it's the question whether Goldstone mode will survive, or if it cannot, could have been gapped. There's nothing that protects it from being gapped, and this is Berezinski-Kosterlitz-Taulus phase transition. Here we can show that it doesn't happen. So the system is always in the gapless state, but a priori this was a dynamical question that could have been answered otherwise. So there is indeed no protection for the Goldstone mode. It can produce a finite correlation length, or it can remain with infinite correlation length. That's a question of dynamics.
Okay. No more questions.